We've got trig to do. Lots of trig. And here is a kind of list of it. We're going to use a product rule. We're going to use a quotient rule. Hopefully you're beginning to memorize, if you haven't already done so, the derivative of 6 trig functions. And here are some identities that get used to make it look simpler when we're finished. So there are 4 main types of questions. The first few are just basically getting you used to differentiating functions that have trig in them. The major bunch, 4 to 12, is trig questions, or questions with trig functions in them that use the product or the quotient rule. Now we do a couple of find equation of tangents, and then the last one is just bits and pieces where applications are. So let's look at the first one. So 3 secant x plus 4 tan x. That would be an example of just differentiating a function with combinations of signs, trig on them. Right. Well, it's basically a plug and chug kind of operation. If you want to differentiate 3 secants, you find out what the derivative of a secant is, which is this guy. So you will get 3 secant x tan x. And if you want to differentiate 4 tangents, you find out what tangent is, and you get the derivative of a tangent is secant squared, so you get that. Are you comfortable with that? I mean, there's nothing, it's just a matter of plug and chug, right? Now, style points. Make it look like the original. Yeah, that's pretty much obvious. Factor the heck out of it. Can you see anything here that can be factored out?
A secant.
Yeah. And that's going to leave you with 3 tan x plus 4 secant x. And then you have a little pause and you say, is there any trig identities going on here that I could use? And the answer is no, there's no trig identities. If there were trig identities, I'd be looking for things like this and this. So if I saw a tan squared plus 1, I'd replace it by secant squared, right? If I saw a secant squared, take away 1, I'd replace it by a tan squared. If I had a fraction and a sign on the bottom, I would call it cosecant and things like that. That's pretty much what questions 1, 2, and 3 look like. Okay, let's do products and quotient rules. So an example of that might be question 4. So we have y equals secant theta tan theta. And this is going to be my f, and this is going to be my g. And the derivative is f dashed g plus f g dashed. If you differentiate a secant, you get a secant tan. Leave the guy there alone. That's your g. Plus, leave the first one alone, just secant theta, and differentiate a tan. Well, a tan is a secant squared. Now, I'll tidy it up a little bit. Secant theta, that's just a single secant, but a tan squared. And that can become secant cubed theta. Okay, so looks like the original, that kind of goes without saying. Anything here that you can see that you might be able to pull out as a common factor?
Is the secant, is there no exponent for it?
None for that one, yes.
You can pull out a secant?
Yeah. And that's going to leave you with, in this case, a tan squared plus a secant squared. Okay, and that's fine. That question is as good as it's going to get. There's no identity. I was just looking at this one in case it was, but it isn't. That you could use to make that nicer. So let's see if I can make one that is nicer. So almost, nah, can't. I was hoping to figure a way of making that simplify more by changing the question, but that doesn't always work out. Okay, so let's look at, for example, question 6. And g of theta is e to the theta with a tan theta take away theta. Interesting. I'm wondering if I might get something interesting out of this. That's F. This is G. So the derivative, F dash G plus F G dash, because it's obviously a product rule. If you differentiate e to the theta, you still get e to theta and you leave G alone. Leave that guy alone and differentiate this guy, and you get secant square theta take away 1. And yes, something interesting did happen. Secant squared theta take away 1. You see it in my little list here? Secant squared, it's x, but x, theta, b, t, dumb r. Secant squared x take away 1 is tan squared. So isn't that tan squared? So it's not maybe the most interesting style point. And now we have that line. Okay, is there any common factor? Can I factor anything out of these two cases?
E to theta.
And nah, that's it. Can't do any better. And let me get one of my many gripes out with. I'll pick Vanessa. Say that to me. What is that?
You say theta. That's how I say it now. Is it? I don't even know how you would regularly say it. Delta?
No. Okay, who can we pick? Dylan, say that.
Isn't that just theta?
Theta, right. I don't know what your ears hear, but this is what I hear. That is theta. It's a heavy E sound. Theta. What I hear from most Americans is theta. That's a very feminine sound to me, right? Theta. Light. It's theta. It's aggressive. So how on earth can Americans screw up a Greek letter of the alphabet? You just say things funny sometimes, at least to my ears. So if you try to do that in Scotland school, they'd all point at you and laugh. No, they wouldn't. Okay, I got it in my system. Why use pronounced theta different is a mystery to me. Except Vanessa's decided to join me, right, Vanessa? We're just going to say it the right way and laugh at everyone else's choices. I'm just scanning through, find another product or quotient rule. Right, let's do a quotient rule. This is question 8. I think it's pretty obvious when it's a quotient rule and when it's a product rule. Fractions are quotient rules. So to differentiate this function, it's going to be f dashed g, take away f of g dashed, all over g squared. Right, differentiate sine, you get a cosine. Leave the other guy alone. Minus, leave the first one alone. Differentiate the bottom. Well, if you differentiate 1, you get nothing. If you differentiate a cosine, you get a negative sign. And then you do 1 plus cosine theta squared, which is fine. Now, if you distribute this, you get cosine theta. Distribute this, you get cos squared theta. And negative sine theta times another negative sine theta gets you plus sine squared theta. And this question, I think, is a good example of why style points can be useful. Okay, it looks like the original. I can't see anything that can be factored, so we're now going to resort to trig identities. In particular, what does cos squared theta plus sine squared theta equal? What's it the same as?
1.
1. Sine squared plus cos squared plus sine squared, right? Same thing. 1. So we now have the cosine of theta plus 1. And you should be saying, oh, that was nice. But we can do better. And sometimes you just have to see a thing in a different order. I mean, for instance, isn't cosine theta plus 1 the same thing as 1 plus cosine theta, right? It's the same thing. So have we got anything else we can do then?
You can cancel the one of the 1 plus cosine theta.
And when you cancel everything, you leave a 1 behind. So what you now have is 1 over 1 plus cosine of theta. So do you see that that derivative can be made a lot simpler than if I just left it like that? Would you agree? That's what kind of calc told us, but we had to do a lot more work, and it's much prettier now. Now that was an example of a quotient rule giving you a really nice answer. Just for contrast, here is a quotient rule where nothing nice happens. And just to be different, I haven't used this a lot. That notation also means derivative, so we're finding the derivative. Top, bottom. Okay. It's quotient rule again. F dash g, take away f of g dashed for g squared. Differentiate the top, you get 2. Leave the bottom alone. Subtract. Leave the top alone. And then differentiate that. Well, differentiating 9 gets you nothing. And negative tan, when you differentiate it, gets you a negative secant squared. And that is over that guy squared. And distribute, you get 18, take away 2 tan x. And this negative times this negative gives me a plus 2x secant squared x all over that guy. And I can't see anything that I can do to make it pretty. So that's the answer. So this one came out really nice. And this one really horrible. You don't know what you're going to get until it happens. I'm going to show you a product rule because it allows me to add an identity that I haven't done yet. Let's suppose I want to differentiate sine squared x. It's a good idea to realize that you can write it as sine x times itself. Would you agree that's what sine squared x is, right? Sine x times itself. Now, because I've written it like this, you see I can now use the product rule. If I left it like that, it'd be kind of hard to know what to do. And no, you're not allowed to do the power rule, add one, differentiate, and no, don't work. So the derivative, f dash g plus f of g dashed over g squared. Well, differentiate this guy, you get cosine x. Leave that one alone, you get sine x. Plus sine x, and you differentiate that guy, and you get cosine x. And why am I doing that? That's it. Now you multiply those together, and you multiply those together, and you notice that these are the same thing. So you get 2 sine x cosine x. I know Izzy came in, so I know you're here, Izzy. So I'm picking on you.
Yes.
You
sir.
ready, Izzy? That guy there is a trig identity, sometimes called the double angle formula. Can you remember what 2 sine x cosine x is?
I'm gonna say confidently, I don't know.
Ah, if you were going to have a guess, what do you think it might be? If you got a guess in you?
I mean,
I mean, you could be wrong. It's called the double angle formula. Might give you a clue. Right. I'm picking on poor Izzy, but just to kind of prove a point. You can write all these guys down, but you're going to spend half your time looking up pieces of paper to find things. Does anybody actually know? Because I bet you're not the only one, is it?
Is it sine squared?
No, but you're close.
Sine 2x?
Yes. This little list of identities is going to grow bigger. Now I put poor Izzy through the ringer, she's probably going to remember forever now that 2 sine x cosine x is sine 2x because it'll bring back bad memories, right? But at least we've got something. You need to be really aware of the major identities. It's just going to make your life so much easier to deal with trig derivatives. You can certainly have this page or a version of this and use it. And hopefully as you use it, you start memorizing some. You don't need to look so often. But it's one of those things you do need to get good at. It's part of the process.
Before
Yes.
you flip the page real quick,
Mhm.
is that supposed to be a minus cosine x, sine x minus, and then is there
This
stuff
here?
missing on this one? Yeah.
That there's a plus, if that's the one that you're
Okay.
not right.
So why is that a plus when it's a quotient?
It's not a quotient.
It's this one's supposed to be product. Okay. All right. That makes more sense.
Oh God, nobody noticed that? I didn't notice it until you pointed it out. Thankfully, I didn't use it after that line.
Awesome. Thank you.
You are good. So this one kind of falls into a kind of special category of how do I differentiate something like this? There are really two strategies. I could just basically make theta one function and then make that guy there two functions and do a product rule. But then I'd have to do another product rule to get that. We have kind of looked at this situation before. Can't you also just think of it as three things multiplied? You don't get a lot of questions where this happens, but it does happen. So, any volunteers for the product rule using F, G, and H?
It's it's F dash GH plus F G dash H plus H dash FG.
Okay. And now, differentiate that, you get 1. Leave the other two alone. Then leave that one alone. Differentiate the sine to get a cosine. And then leave that one alone to get another cosine. And I don't have room, so I'll put it down here. Leave the first one alone. Leave the second one alone. And then differentiate a cosine to get a negative sine. So let's see what we get. We get a sine theta, cosine theta, plus a theta cosine squared, minus a theta sine squared theta. And there is no factoring that I can see. And there may not be any obvious trig identity, but there is. Remember this guy, the double angle? There's another one. Cos squared x, take away sine squared x. And that is the double angle formula for cosine. They are quite different looking at, aren't they? The sine of 2x is really a product, and the cosine of 2x is two square things. But notice it's subtract, not add. So, I'm going to do this really slowly. I'm going to pull out theta as a common factor. And it's only a common factor for the last two terms, which seems a little bit unusual, but we'll do it anyway. Cos squared theta take away sine squared theta can now be written as the cosine of 2 theta. So haven't I used a trig identity to make it look pretty? Now this one here is a hidden trig identity, because you go over here and you say, oh, if it had been 2 sine theta cosine theta, right? If there'd been a 2 here, I would have written sine of 2 theta. But there isn't a 2 here, right? It's not there. But I can still get an answer. And it's the half of the sine of 2 theta. And I'll do that in a little, I'll do it down here. That guy is what the sine of 2 theta is. If you divide this guy by 2, then sine theta cosine theta is the same thing as a half the sine of 2 theta. So do you see that these trig identities are appearing everywhere, and they're going to make your answer quite different from what it might originally look like? And depending on how fussy WebAssign is going to be, it may not accept this answer, right? So you have to be kind of vigilant about that. And that is pretty much the second one on my list. Done. I've done some examples at least of product and quotient rules. Now we're going to move on to number 3, which is finding the equation of a tangent line. And there's only a couple of them. So one of them is question 13. And we have sine x plus cosine x. And we're being asked to find the equation of the tangent line at the point 0, 1. We've done tangent line questions before. I'm going to approach this the same way. First thing I'm going to do is differentiate. And the x coordinate is 0 here, so I'm going to find the derivative at 0 because that's going to give me the slope of the tangent line. So in this case, it's cosine of 0, take away the sine of 0. And the cosine of 0 is 1, and the sine of 0 is 0. So that means the slope of the tangent line is 1. And I know a point on the line, that guy. And I'm going to call this guy x1, y1. And now I can use the point slope equation. Y take away 1 times x take away 0. That is the equation of your tangent line. In a lot of ways, isn't that exactly what you do if I ask you to find the equation of the tangent line of x cubed, you know, at 1, 1 or something, right? You find the derivative, you evaluate the derivative at the x coordinate of the point. In this case, you get 1. You then use the point slope equation to finish it off. So what can go wrong to make these questions harder? Can you imagine that it might be in something like that? You are going to have to find exact values for things that look like that. How do you find the exact value of sine of things like pi upon 4 or cosine of pi upon 2? How do you find the exact value? You can't go to your calculator. All you'll get out of that is 0.707. I'm looking for the thing I want to show you. How do you do it? Any takers for a show you? Unit circle. Yeah, unit circle. So if I wanted to find, because you know this thing up here had the sign in it, right? Suppose I went and said to you, oh, I want to find the answer at pi upon 4. Wouldn't I have to find the cosine of pi upon 4, or the sine of pi upon 4, whatever it should be? So if you want to find the sine of pi upon 4, there it is. In this case, the sine is the x coordinate, so it's root 2 over 2. And if I want to find the cosine of pi upon 2, here is pi upon 2. And the cosine is the x coordinate, so that would be 0. If I wanted to find, say, the cosine of pi upon 3, it would be this is pi upon 3. And is the cosine the x or the y? What is the cosine of an angle? The x coordinate of the unit circle or the y coordinate from the unit circle?
It's the x value.
In this case, it would be a half. So you might, if you're going to do one of these tangent line questions, can you imagine that you might get an angle a lot easier than 0 or a lot harder than 0, in which case you go hunting for a unit circle. Hopefully you've got one. And can't you just get the answer off this? And that is kind of all I want to do with tangent line questions, because there are only 2 of them. And the one that I haven't done is a little bit harder, and the point happens to be a slightly more ugly place, which is that. But the method I showed you is the same. So let's move on to the last set of questions. which are the applications or puzzles. First one is question 16, and they give us a pretty nondescript function, which is this guy. And they ask you to find its derivative. Oh, let's put you under pressure. Anybody memorized yet the derivative of secant x? I'm doing the easy one. Derivative of x is -1. Anybody got the derivative of secant x? And I don't mind you getting it wrong, because at least you're trying, right? What do you think it is?
Secant times tangent.
And you are correct. Now, what else are you going to do? These are, this particular question has two pieces to it, which I think I'm going to just show you because it's very visual. The first piece is you're then going to put, using Desmos, the function and its derivative and compare them. So that was question 16. Check that one. Now, the original function would be secant x take away x, and the derivative, which is the one we just found, was secant x tan x -1. And evidently, I have screwed up with lots of brackets. There we go. Oh, one more bracket.
Sometimes it automatically adds a bracket.
Even when I don't want it to. There we go. Okay, I guess avoid brackets around x's in WebAssign seems to be, it has its own ideas of what should have brackets. Now, there are 4 pictures here. Now, you can certainly type in secant x minus x into Desmos, and you can type this one. And isn't it just a matter of looking at your pictures and seeing which one is the same as theirs, right? You're going to make your window from negative pi upon 2 to pi upon 2. Remember that little curly bracket thing that allows you to do that? Well, let's try it the hard way. Has anybody got any ideas which one of those 4 is actually the right combination of pictures?
Well, it has to cross through -1 at the origin. Or at the x equals 0 has to be -1 for the derivative function. So it has to be either this one on the right or the one below.
That was a good thought process. I like that. Let's just leave you to do it. That's more fun. And they get a little sentence there for you to worry about. So Desmos makes it easy. So I guess, to be honest, wouldn't you just do Desmos and say, okay, I'll let it figure it out, because it's hard to tell sometimes what a trig function is going to look like. But I do like your thinking. What I was going to do is I was going to look at where 0 derivatives would be, you know, what, because if you've got a happy face, isn't there going to be a 0 derivative at the bottom of the happy face? So I would just look at which picture has a 0 there, and hopefully there's only one of them, and that would be my answer. But I like your idea of -1. That's a different approach. Well, what do we have for our next one? Well, here we're going to have multiple derivatives. You are being asked to find in question 17, not just the first derivative of secant t, but its second derivative as well. Now, first derivative is secant tan. Second derivative is the derivative of secant tan. And we will use a product rule. Right, if you differentiate a secant, you get a secant tan. And then you leave the second one alone. Plus you leave the first one alone. And if you differentiate a tan, you get a secant squared. So actually I'm getting deja vu here because I think one of our earlier questions today was exactly that. Okay, style points. Anything you can do to this? Remember
Or
what we
the
did?
secant.
Yeah, there wasn't anything much except the secant. You're right. And just, you know, like in the monster movie, just when you think they're safe, that it's done, the movie is over, they stick this in. And that means unit circle. So let's find out what the second derivative is at pi upon 4. Well, it's going to be the secant of pi upon 4 times tan squared of pi upon 4 plus a secant squared of pi upon 4. And not only is this going to be a unit circle, just to make life even harder, we're not even going to be able to use these numbers directly. We're going to have to use them indirectly. What do I mean by that? I need to know what that is equal to, and it's going to go there and there. And I also need to know what that is equal to so I can use it here. Well, there are no secants in the unit circle. There are sines and there are cosines, right? The x is the sine, and sorry, cosine is the x and the sine is the y. So if I want to find the secant, I have to realize that it's 1 over cosine. That's what I mean by you have to do it indirectly. Now I can find the cosine. Isn't the cosine root 2 over 2? So this is 1 over root 2 over 2. Essentially, it's reciprocal. So there we go. 2 over root 2. So I can now go 2 over root 2 here and 2 over root 2 squared here. Now, if I want to get the tangent, I have to figure it out as the sine of pi upon 4 over the cosine of pi upon 4. And this guy is the y coordinate, and this guy is the x coordinate. But for pi upon 4, it really doesn't matter since they're both the same number. And since they're both the same number, won't the tan be 1? But won't it matter more when you get the tan of pi upon 6 or the tan of pi upon 3, right? In that case, that will be important. So I know this is 1 squared. So let's hide that guy because we've kind of used them. Now we do a little more tidying up. 1 squared is 1. If you take 2 over root 2 and you square it, you get the same thing as 2 squared on the bottom and root 2 squared, which is 2 on the bottom. And now you have 2 over root 2. You have 2 over root 2 times 3, and that gets you 6 over root 2. So far, so good. I'm pretty sure WebAssign would probably accept that, but if we want to be really fussy, couldn't we rationalize the denominator so the square root of 2 is not in the bottom? And that gets me 6 root 2 over 2, and a little cancel. There's the best answer in the world, 3 root 2. So that application or puzzle was finding a second derivative, and then they stuck a, but get the answer at a particular point. In this case, pi upon 4. Okay, almost finished. Question 19 doesn't look particularly weird, but it's phrased, for what values of x does the graph f have a horizontal tangent line? Well, aren't horizontal tangent lines 0? So essentially they're saying to me, find the values of x that make this derivative 0. So first I need to find what the derivative is. It's going to be a product rule. And that guy gets you e to the x, leave him alone, cosine x, plus e to the x, differentiate this guy, you get negative sine x. If you pull out e to the x as a common factor, you get that. And we are trying to find when is the derivative 0, which means we need to solve this really weird looking equation. So first thing I'm going to do is I'm going to ignore e to the x. It's not going to generate a solution. And the reason for that is that e to the x is never 0, right? If you sketch e to the x, it's always a number bigger than 0, right? It just goes uphill. So our question becomes a little bit simpler. So now we have to think back to when we solved equations in Trig. And there are different ways of approaching this, at least 2 that I can think of. So here is one version. I'm going to add sin x to both sides. And then I'm going to divide both sides by cosine of x. That is going to be 1. And what's sine x over cosine x?
Tangent.
Tangent. So what I've managed to do here is turn it into a trig equation where there's only one trig function, in this case the tangent. So if I use my unit circle, will you agree that at pi upon 4, the tangent is 1, right? The y over x is 1. Now, they didn't put any restrictions on it. Can you remember that plus or minus k pi thing? You know, where you could add pi and get another answer and add another pi. When it's sine, don't you add 2 pi? So if it was a sine question, it'd be plus or minus 2 pi k, right? But when it's a tangent, the period is pi, so it's plus or minus pi k. So that's the answer to that one. Actually, that is the answer to that one because there isn't any variations. So everybody's question 9 looks like that. Our last question, perfect timing, I think, is you are told the position of a spring is given by that function. And they even show you a little picture, a little spring like that, and there's a weight and it oscillates left to right, and t is time and x is its position. And we are being asked to find the velocity of that spring at t and the acceleration. So that's the position function. Normally, don't we call that s of t, but in this case, it's called x of t. Don't need to know the answer, but how do you find velocity when you know position? What do you do to this guy?
You find the derivative.
You do. And velocity is the first derivative. And to get acceleration then, don't you find the second derivative of this guy or the first derivative of the velocity, because it's the same thing. And if you differentiate this guy, you get -4 sine t. So that question was not that hard once you realize that velocities are first derivatives and accelerations are second derivatives. And then they do in part B, and they ask you to find the position, velocity, and acceleration at, in my case, 2/3 pi. Well, I'm going to be looking for the position. I'm going to be looking for 4 sine 2/3 pi. For velocity, I'm going to be looking for 4 cosine 2/3 pi. And for acceleration, I'm going to be looking for -4 times the sine of 2/3 pi. And isn't that where the unit circle kicks in? Right. I need to find the sine of 2/3 pi. It's over here. Right, there's 2/3 pi. Which one is the sine? The -1/2 or the √3/2? Which one is the sine? The x or the y?
It's the y, right?
Correct. So it's 4 times √3/2, which is 2√3. The cosine is the other one, so that's -1/2, so that's -2. And this guy is basically just that guy with a negative in front of it. And that's the answer to those ones. Now, since the velocity is -2, and in particular, it's negative, they ask us a question that just seems a little bit strange. The mass of the object is moving, and they give you 2 choices. It's moving left, or it's moving right. Now, can you imagine this little spring up here? It starts off there, right? And then I stretch it, and it goes like that, and then it goes in the way, and then it comes out the way, and then it goes in the way. If it's moving that way, the velocity is positive, and if it's moving this way, the velocity is negative. Does that make sense? That if you go to the right, it's positive. Now, since this was a negative, doesn't that mean it was moving left? And if the spring had been turned upside down, you know, and pulled this way, wouldn't up be positive and down would be negative? That would make sense. We are done. Stick a fork in us. Get a copy of Unit Circle. I think I've put somewhere in Canvas, you can print it. Start memorizing these guys. Start getting comfortable with trig identities. The more you use them, the more you get comfortable with them. And I will see you on Monday.